Okay.
Yeah.
And it looks very, if you've ever used Mathematica, it actually has a very similar feel to the Mathematica notebook interface, which is this kind of input-output cell.
So it could be a cool way of, if you're teaching a class, right? You could have all your stuff in there, and then you can work with it, not having to go find it, pull it in, or static.
Yeah, you should look at some of the stuff Cloud Sharper is doing, because they're actually tackling that problem.
Huh. Seems like people are tackling problems faster than I can find them. I didn't know that was a problem until now. Tell me.
That's the world we live in now.
Yeah.
Especially if you're chasing JavaScript frameworks.
Yeah.
Not as much, I would say. This year,
Yeah.
seems like it's off to a slow start, right?
Yeah, no, that's the operative thing. If you say, like, if you ever have to say, like, this year, you know, as being
Only in the past month.
yeah.
Well, you know, the
Slowed down.
unfortunate casualty of that is that people like me, where I'm not working in a UI situation all the time. Right? Every time I do some work, it's just radically different. You know, it's like I come out and MVC3 is like totally gone. And do this thing. Oh wow.
Yeah.
So it can be really daunting. Fortunately, I've got people that come into my life. You know, like Jim's showing me, okay, this is how you use Angular. But I'm afraid to learn too much because the next time I have to go back, we'll be using F# in the browser. Could happen. I'll just keep.
Had the same experience of realizing that, I learned something and now that's not relevant anymore.
When the UI thing is so big, you're stuck in the framework. It'd be a huge effort to.
That's right. You kind of like get invested in something, and depending on where you're at with it, if it's a small enough thing, sure. But if it is big, you have people start throwing around that big 3-letter word of ROI.
Right.
You waste a lot of money in meetings.
Yeah.
Does everyone have the Wi-Fi password? If not, it's in orange. It's INCWL.
Yeah, at the end of this, I'll have because I expect this will only, the presentation should take not too long. And then at the end, I have the GitHub locations for the code that I talk about, and then some suggestions for things you can do to play with the basic concepts here. Try to come up with exercises that went from kind of I have never done F#, and these are relatively simple, to I claim to be an expert functional programmer, so here's a complex thing that will be hard to solve.
And I also have to pitch us. We are still hiring, as always. We're growing. We're about to take over the rest of the floor. So if anyone's interested in talking about that, we can do it after. We at the .NET shop on the server side, and Angular, JS, UI. So, yeah, if you're curious, I'm sure most of you have been here before, it's real, but we deal with stored values, so anything from prepaid phone cards to gift cards to Visa cards that have cash on them that are reloaded, and everywhere in between. For a lot of different brands. And if you're interested or curious at all, just let me know. We can talk about it and I can show you our different job openings we have.
Well, is there a certain like event that's like spurring all this growth? Or?
No, we're just it's a growing industry, and we are, from what I've been told by the business side of things, we are the easiest to integrate with and support the large number of brands, etc., and all the mobile wallets that are out there are integrated with this. So Google Wallet, eBay, PayPal. We've never said on Apple yet. Yeah, I mean, we're creating an RESTful API that they can all consume, and then we also have UIs that are different browser and browser applications. So if any of you are kind of curious, incomeincentives.com is one of the latest sites we've released that uses our API. I think that API can be consumed by anything. So the application in browser is deployed to AWS, but it's hitting APIs against their server. And all Amazon does is load HTML, JavaScript, and CSS, and PDFs and images. It's that.
Nice. Well, let's go ahead and get started. That way, anybody who's listening online is just listening to our banter here.
Yeah. Okay. So the 1 minute thing's passed. He's
1
ready.
minute things pass.
Okay,
we're
cool.
good to go.
Okay, so so I guess in November when I attended one of these, I kind of made the offer to give a quick talk on something I've talked about before, which is basically how one goes about using languages like F# to implement domain-specific languages. It's something I do a lot in my everyday work, and it's one of the things that brought me to functional programming, and so it's always something that people seem to enjoy learning about. Just a quick bit of information about who I am. So my day job is I work at this company called Galois that's just a couple blocks from here. We're a functional programming shop, primarily Haskell focused, but we work in a lot of different functional languages. And then the new little startup that I'm working on is at Sailfan Research, and that's the one that's going to be using F# to some degree, largely for computational things. And I also kind of put an academic hat on periodically, and I'm an adjunct up at Washington State University in the computer science department. So some of this may come off feeling a little academic since it's derived from work that I did when I taught. But it's hopefully grounded in some practical things. So the basic overview of the talk is I just want to, it's not going to go into a lot of deep detail about F# because I assume people would be somewhat familiar with the syntax, but what I want to do is point out what goes into designing domain-specific languages, like what is the design space that you want to be thinking about, especially in terms of how that relates to languages like F#, and then what kind of decision you'd make in terms of how you'd implement it, whether or not you embed the language in F# or if you try and build a proper domain-specific language that's a standalone. There's interesting decisions to be made there. And then I'll walk through kind of what are the major building blocks or major language features from F# that are kind of the things you want to be aware of if you're putting together custom languages. And then I prepared two little baby domain-specific languages that are partially incomplete that people can work with and kind of manipulate them, add to them, change them, break them, or at least look at them. And those are all on GitHub, and I'll put the URL up at the end. And just a little warning there is, domain-specific languages are kind of a hot topic in the programming languages world. If you follow PL research, a lot of people are doing DSLs. And so you'll see 10 people doing it with 10 different opinions about them. And so these are mine. None of this is what I would consider to be canonical or the right answer. It's just my perspective on the topic. So, the key thing about a domain-specific language is it's a language that's specialized to a specific purpose. They're not, so examples that I've run across are like hardware configuration languages. So a language that you hand to something like a Cisco router that tells it how to lay out the routing tables. It's very good at that, lets you write, has syntax specifically for writing down routing tables, but has nothing related to other computational tasks. Cryptographic languages, things to write down, things like AES encryption. Very good at that, allow you to build very efficient code from it. You wouldn't use them to write a game. Build systems, so Fake, the F# make system. That's a domain-specific language. It's actually an embedded domain-specific language in F#. And it's a language that's specialized around build. A common theme around DSLs, though, is that I think the reason people give them special attention is that they tend to not be like traditional languages where you build up all the infrastructure yourself. So if you're writing a C compiler or C++ or Fortran, you're going to write everything, whereas DSLs, you typically start with a base language and then just do whatever necessary work you need to do to build the new language on top of it, and then reuse all the existing infrastructure from the other language. So the sorts of things that go into designing a DSL, like what you want to think about are, first off, what are the data elements? So what are the things that you operate on? So in network routing tables, it's things like packets and the routes themselves, the hosts in the network. Once you've decided what the pieces are that you want to manipulate, then you start coming up with the operators. And so these would be being things like if you're dealing with routing algorithms, an operator that you may implement in the router is a filter. And so you may say something like, oh, anything that comes from this IP address reject. And so that would be an operator in the DSL for building routing algorithms. Then you start looking at things like combinators. And so combinators are ways of combining things together. And so in functional languages, when you see things like higher order functions, so map. So map is a combinator because it takes another function and applies it to something else. And so combinators are ways of taking smaller pieces of code and then combining them together to make more complicated pieces of code, that then those can also be composed, and you kind of get ever increasingly complex programs. Once you've worked out kind of what the data elements are that you're working with and then what you want to do to them, then you start worrying about semantics. So what do my programs mean? And then at the final step, you worry about, okay, what's the syntax? How do I express this? I intentionally laid it out this way because classical DSL talks always frustrate me because they all start at syntax. And they all basically people get really deep into parsing and parser combinators and all these things like that. And they forget about the fact that a language syntax is really the least important part. You really have to work out the semantics of what it is you want to represent and what you want to do to it. And then you put the syntax on once you've got that all worked out. That's one of the things that some people may disagree with me on. Once you've worked out kind of these pieces of DSL design, one other decision you want to make is what kind of DSL is it? So is it an embedded DSL or a standalone DSL? So, and I forgot to mention, if you have any questions or comments, just speak up. I don't need to not be interrupted. So an embedded domain-specific language, that's like fake. That's an EDSL. And the point of an EDSL is that you don't actually create new syntax from scratch. You actually leverage an existing language that is built to be customized, and then you add syntax to that existing language, either by creating new operators or creating new functions that act like operators or act like keywords, but in fact are actually just functions in the host language. The other type of DSL are the standalone languages, and these are the ones where you actually provide specialized syntax. And those are the ones where you have to work out not only what are all the data elements and what are the program structures, but what are the syntactic elements that get turned into like the abstract syntax structures. Those are harder because they basically require you to think about everything as well as the parsers, but there are reasons why you would end up using those. And as I said, more often than not, I go the EDSL route because it makes me think about these top four things. The what is it I'm going to operate on? How do I operate on it? How do I put stuff together? And what does it mean? That's usually most of what I'm inventing a DSL to do. The thing with EDSLs is that you're not worrying about the syntax. So you're not worrying about the syntax, but the subtler thing, and this is actually a topic that you'll occasionally see talked about in the active programming languages research community, is this problem of error reporting. And so syntax error reporting. So if I write an EDSL that's embedded in another host language, and somebody makes a syntax error, that's a syntax error in the host language. And so if it's an F# language, and they think they're writing in a new DSL, and they do something wrong, they're going to get an error message that's actually at the level of the abstraction of the host. And so that can be very frustrating because you usually make DSLs for people who may not know the host language. So you may provide a DSL for router configuration that's intended to be used by a sysadmin, and they may be able to understand errors that talk about like invalid routes or invalid port number. They won't understand things like the type not checking, or there being an unsatisfied or a non-exhaustive pattern match in something. So EDSLs that is something that they suffer from, and no matter what language you embed them in, this percolates to the top. In Haskell, we see it a lot because Haskell produces some really bizarre error messages. And when we've done EDSLs in Haskell, people get quite confused. And so EDSLs are good if you're working out all the details and you know you're dealing with an audience that won't get terribly intimidated by the syntax error reporting. But if you're designing a language where you actually have to worry about kind of the end user experience, that's where the decision of embedding or not becomes a important thing. Yeah, so I just talked through that. So, any questions? So we're all here because functional programming, for whatever reason, was an attractive, interesting thing. And so what is it about functional programming that's attractive, especially for DSLs? And when I looked at it, fundamentally, where it kind of comes out is the functional languages, well, let me qualify that. Strongly typed functional languages that basically come from the ML family have very rich type systems that are very, once you get used to using them, it's very frustrating to not have them. And so this includes F#, OCaml, Standard ML, Scala to some degree, basically everything outside the Lisp family. And people can argue that you can bolt type systems on that, but the ML family has beautiful type systems. They're also very good at symbolic manipulation, which is actually what compilers, interpreters, and other language-related things do. You never push numbers around for the most part. You're just taking trees and making them into other trees, and sometimes you take the trees and turn them into graphs, but it's mostly just pushing around symbolic things. So they're very good at that. And they also give you all this runtime infrastructure for free. So like they're garbage collected, and they have nice memory management. So the type systems, so what is it about them that's really cool? So the thing that got me hooked on ML the first time around was the type inference system. So Hindley-Milner, that's what HM is. The Hindley-Milner type system that they use, that's the algorithm that's used for basically letting you write down untyped code and it infers what the type should be. It's very powerful from a kind of expressiveness point of view. So I can write down code and I can ignore types if I don't want them. And it'll tell me when I actually need to give the compiler some hints because it can't figure it out. But it's so from a first point of view, it's a convenience thing. It's like I don't have to type as much. Compiler figures out stuff for me. And that's kind of the view that the C++ people took when they introduced the auto keyword. So you can say, I don't want to type the type, and it's okay. That's eliminating keystrokes. But strong type inference like Hindley-Milner is actually deriving a proof that the program has these types. And if it can't derive that proof, that's when it gives you an error message. So having a type system like this means that you're essentially getting a formal verification of your program for free. And so if you build a domain-specific language in the type system of a functional language like F#, when the F# compiler can verify that the types are sound, there you go. You actually have very high confidence that your types are sound. And so it gives you some pretty strong assurance about the program. So your DSL gets that for free, which is pretty awesome.
So how is that different than the auto keyword?
The auto keyword, I don't believe... so I don't believe it's actually doing full type inference the way like the Hindley-Milner algorithm tells you, like the way that actually works. I think it's doing
runtime, or is it compile time?
No, it's a compile time.
It's inferring though from the return result of whatever it is on the right-hand side.
Yeah, it's like a very basic use-based thing, but there's no concept of. So in Hindley-Milner, you can have alpha type. So you can say a function is alpha to beta to say these are actually it's going from generic type to generic type, and that I don't think the auto keyword will give you. I don't think it has a concept of these kind of placeholder types, and that's very powerful when you're dealing with things like combinators that are functions on functions. So you want to be able to have the type system include these placeholder types. Is it clear? Does everybody here know what the kind of alpha type is? So an alpha type, well, alpha is just the placeholder that they put in there. But if I have a function,
it's like generics in C#.
Kind of like the map function. So the map function, its first parameter is a function of some type A to some type B, and it takes a list of type A and produces a list of type B. And so the A and B there are just placeholder types that can be anything, and it just says that they don't have to be the same.
So it's very similar to
Yeah, yeah. And so it's kind of cool. And the fact that the type inference system can look at the way types are used, and it can determine that, like map would have the type A to B, whereas it would infer if map had a different structure, like if map was, well, if it just took the input and gave it to the output, it would be able to infer that actually the input and output type are the same, so it would say it's actually A to A. So it's kind of cool the way it infers these relations between types, not necessarily having to be concrete types. So that's very powerful. This was what got me addicted to standard ML. So the next thing when kind of thinking about the DSL side of things is this concept of symbolic programming. So DSLs, language things, it's just manipulation of structures, trees or graphs. And if you think about like, okay, so I have in C or C# or some other language, you can imagine coming up with data like classes that represent nodes in a tree. And that's not that hard. Now I want to say like, find patterns in the tree. So find every case where you have a node of this type and with a child of this type on the left and another child of this other type on the right. writing that pattern matching is actually, you'd have to do a lot of manual bookkeeping to tell where you are. Whereas the match keyword in F# allows you to write that down in one very concise line of code. And so things that would be actually quite verbose and potentially error-prone in another language is actually just a built-in primitive in a language like F#. And then the things that you match on, these algebraic data types or discriminated unions in F#, those are kind of the entity that you combine with the match keyword to actually match, to express the structures that you then want to match over and transform. And so I think it's the fact that it's very expressive and compact means that you can start. When I've seen people work on designing DSLs, a lot of times they start on the whiteboard and they write out kind of what the structures of the program should be. And this almost allows you to translate that directly into text, whereas translating that into C++ or C# would be the whiteboard to code path is a lot longer. And also, again, the type system here keeps you sane, and it makes the manipulations somewhat safe. It's harder to do stupid things in terms of how you manipulate the trees because a lot of times a stupid thing won't type check if you designed your AST correctly. And finally, you get this infrastructure for free. So you have the memory management and the garbage collectors. You have closures, so the concept of being able to partially evaluate functions, or not partially evaluate, partially bind functions. That's just something that's there for free. The fact you could pass functions around as data, that's what lets you start building up combinators with virtually no effort. And the pattern matching, that is also a very useful thing. So based on these bits and pieces that I claim are what makes FP attractive for domain-specific languages, this is kind of a non-exhaustive list of what I think are the top building blocks that I think are quite useful. So the first one, I think, that is the building block you need to get comfortable with is the use of discriminated unions for representing your structures in your program, because those are fundamentally the thing that the program is represented as. It's the thing you're going to traverse. It's the thing you're going to transform. It's the working unit of the program. Following that is pattern matching, because that's how you work with those things. Then the other things here begin to get into discriminated unions of pattern matching. One could argue you actually have enough building blocks there to get really dangerous in terms of building DSLs. But you're still going to be forced to have the host language syntax in its unvarnished form. And if you're building a DSL, you do want to start exploring ways of expressing operators in a concise manner, because eventually you may get some syntax that's standalone. And so infix operators are a way, and operator overloading are ways of basically making new operators and then making them look like, to the DSL consumer, first-class citizens in the language. So you'll see a lot of times in DSLs bizarre-looking operators like greater, 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 equal, or greater dot something. And those are just infix operators that people have come up with, and they have a very specific meaning about what they do to the AST of a program. And my little demo has some examples of those. Those make it so that actually you can actually push infix operators pretty far in operator overloading to make your code make it look a little bit like a native language. It stops looking like you're putting AST parts together by hand. And one of the final ones is if you really want to get serious, you can start using things like computation expressions, which is a very convenient notation in F# that essentially allows you to hide a lot of the behind-the-scenes plumbing. It lets you kind of string some data structures behind that you don't really want to see. And I have an example of how that can be used as well. And so if you put those things together, you actually can get code that begins to look very much like a standalone language that's completely embedded in F# that can be quite expressive, and you can tune its expressivity depending on what the problem is you're trying to solve. Two other things that are worth noting, but I don't talk about at all. So active patterns are another one. That's something that F#, I think it's somewhat unique to F#, and that's essentially a way of kind of, I'm probably going to, so F#, people who know F# better than me are probably going to say I'm going to butcher them, but I kind of look at them as almost a way of creating discriminated union members on the fly, kind of dynamically, where you can say, well, this, like one of the examples I've seen is like something where you consume strings, and then if the string is an int, so you have a function that says, oh, if it's an int, then I'm going to return capital int I with the actual value, and then then you can create another one that works on strings and turns them into floats, and then you can pattern match on those as if you had created a discriminated union that had all of those as distinct instances. So that's how when I've read things about them, I've never used them in practice, so forgive me if I butchered them to the people out on the web. The other thing that's worth noting is this concept of code quotations. In other languages, sometimes that's called quasi-quoting or metaprogramming. And that's basically manipulating F# from F#. And it's a very, very powerful way of basically saying, I'm going to build code that will... So pattern matching and discriminated unions allow you to make your own AST and manipulate that. Code quoting lets you then work on F#'s AST itself. So you can basically sit there and say, oh, I had an F# program that was calling this function, and so I actually want to change where it calls add to multiply. And so you can write an F# function that you give it some code, and it rewrites it into that. So you can get quite dangerous in terms of manipulating F# code using code quotation. And that's another way of getting really fancy in terms of how you do your embedding. Because you can basically control at a much finer granularity how your abstractions are being translated into the base language. But that I played with it for a couple hours and thought, okay, I'm getting myself lost. I can't teach that. But there are interesting tutorials on how to use it. So I'm just going to walk through each of these. So this is okay. It's gone now. So am I ready to go?
I'm asking.
But yeah, GraphViz is like one of the first things that I write backends for, because it's a very easy language. It's just string, arrow, string, semicolon, string, arrow, string, semicolon, and then assuming your strings match, that's how you connect things together. And so you can actually look at your AST as a graph. And for some cases, not that little one, but I did a language at one point where it was like a Fortran derivative, and it didn't work very well. And so I ended up getting these gigantic GraphViz visualizations I would print and then go through by hand. And it was, the fact that I could write a back end for my DSL to do that was nice. So pick up on. So I think I had gone through most of this when we died the first time around. So basically, discriminated unions are kind of how you build up the things that you're going to operate on. It's very compact notation relative to the equivalent in other languages. And also, you traverse it using pattern matching. And so that's where you begin to feel pretty powerful. But also, it's type checked. And so the type checking part becomes really helpful when, in two cases. So functional programmers, I don't know if anybody here has gotten into this habit yet, but a lot of times when I want to refactor code or change it, I actually change it and then try and compile, because then the type checker will tell me all the places now my types are screwed up. And then it gives me a list of every place I need to go through the code to fix it. And so the fact that I can manipulate my AST and then let the type checker tell me where I broke it lets me have some assurance that the change has at least been dealt for everywhere it has to be dealt with. And the other thing is I can add instances to these types, and then the type checker will also tell me if I have a match that's not trying all of them. In other languages with like switch statements, you don't get that. So you can kind of dangerously not notice something and explode later when you fall into the default clause. So once you have the AST, the pattern matching syntax is how you interpret it. And this is so this is written in terms of the other the types on the previous slide. So what you end up doing, so this is like an evaluator. So you give it an expression, and we'll go through the expression and evaluate it. What you end up doing is you say, so what comes into this function is expressions. So this E is something of type EXPR. And now E can either be a binary operator or a constant. And so the pattern matcher will say, okay, whenever I see a bin op, that's going to have 3 children, and I'll give them names. So I'll say bin op will have a child called op, E1, and E2. And then the body of this particular pattern, I could say I can then determine what I do with that. So in this case, somewhere else I have a function that knows how to evaluate binary operators. And so I can say, I'll call that, I'll tell it what operator I want to work with, and I'll hand it the evaluated children. So I'll recurse into the children, evaluate those, take the result, and then give it to the binary operator interpreter, to do something with it. And then if that doesn't match, I fall through to the constant and say, okay, if I see a constant, the constant's body will be C. And then I can nest these because I designed the constant to have either floating point constants or integer constants, and then I can just put another match in there. And this lets me take apart the floating point constants or integer constants. But what I'm doing here is basically my decision is I'm always going to work with floats. And so if somebody pushes an integer constant in, the way you interpret that is an integer constant is just turned into a floating point number. If I had a floating point constant, I don't need to do anything to it, so I just let it pass through. And so you can imagine if I eval constant fconst 4 dot, what would come out of it would be a floating point number, 4 dot. And so you can imagine the type of this thing, it takes expressions in, but because this one here is returning floating point numbers, all of these clauses have to return floating point numbers. So you can infer, and this is sort of what the type inference engine would do, is that bin eval, its type is going to be binary operator to float to float to float. So this thing will evaluate things and produce floats. And then in this case, I actually put a bottom case of I couldn't match anything. So if I don't match anything, it will fail with, it'll basically say some expression type that I didn't know about was encountered and explode. If I left this off and I had a third type of expression, the compiler can tell me non-exhaustive pattern match. You need to do some more work. So that's pretty useful, and it's a lot more sophisticated when you start working with it than just switch statements. There are tricks that you can do with switch statements, dirty, unholy tricks that you shouldn't do, that you can't do with these. So you can't do things like fall-through statements. So in case statements, you can say like case 1, do some stuff, forget the break. Case 2, do some stuff. That's dangerous, and you can't do that sort of thing here, which is kind of a good thing. You have to think a little bit more about how you design your cases.
But isn't the bottom, how is the bottom case different than, isn't that catching the starter thing?
That's basically default.
So I guess so how is that different than the case example you were talking about?
I'm talking about the case. So in case switch statements, it's not uncommon to see people leave out the break statement.
Oh.
So that's the thing that's supposed to say, I've dealt with this case, I'm breaking out and leaving the switch. But you can write things where you leave the break off and you fall through to the next one, which people will do. Bad people. But it's because it's very hard to debug programs that do that sort of thing, and so you can't write those kind of tricks via pattern matching for a very good reason. So yeah, but it's also so the cool takeaway things to get out of this is not only the fact that you're matching on the structure itself, but you're also pulling the structure apart. So when I match on a bin op, I'm not only matching that there was a bin op there, but then I'm pulling apart what its children were, giving them names, and then I'm able to use those names directly here. And you can actually write these things where you can like pattern match on a bin op that contains B+. And so I could actually have a case just for pluses. And I could have actually gotten rid of the bin eval and had all of those enumerated here and actually do the addition and subtraction and multiply. And I showed a little bit of this in the other language example, but once you've got these building blocks, so this is what you represent. This is how you walk it. Now it's how you put it together, how you assemble the structures. And so the infix operators are kind of, if you don't have these, you put together the types by writing stuff like this. So you have to explicitly say, I'm going to construct a discriminated union of type bin op. I'm going to have a B+ in there, and then someplace else I'll have the other children. But that can get kind of verbose and really unpleasant to work with. Your code will start to look like Lisp, actually. And so bringing in things like inline operators allow you to add syntactic sugar on top of the actual representation. And so you can write stuff that begins to look a little bit more like what you probably intend your language to look like. And in this case, because of the way I did the constants, so in this case, like I wanted to make it so I don't have to put all this in to put a floating point constant. So you can start also using functions that hide the fact that a simple function will actually be constructing a more complicated bit of AST for you. And I think if you probably wanted to, you can get away with doing things like type overloading or operator overloading, where you can start saying, like, if I see a floating point number being used with a instance of expr, then I actually can call something else that'll lift that floating point number into the tree. That's a topic, though, that you get into that once you feel comfortable with everything else. And that's one of the cases, actually, where I think you can start using quotations to help you out a little bit.